Need to be reminded if I don't to hit record, which means you do need to stay quiet during the actual lesson part of the lesson because I need to come through to the recording. So make sure you are paying attention, you are quiet throughout the entirety of the lesson. So welcome back. For those of you who weren't here, we did have an exam, as you know, last class, and you know that you are responsible for making up said exam. So no pressure, but the rest of the class did the best I've ever seen a class do. There was not a grade lower than a C on a raw score. So I'm really happy with that. You're on a good track so far. Very positive, very good. And even a C score is actually a good score. Like, generally speaking, a C is okay. Because it's curved on a Cambridge, that's still with a Cambridge curve, but that's actually not so poor. What you don't want to get is like a 20 or 30% of the grade book. That's like a freak out. 70 or 80 in the grade book is actually not bad at all. So you have to change your perspective a little bit. There were also several grades that were over 100%. So I believe the top was a 110. There were 2 students that got a 110 in the class as a raw score.
That's great.
So anyways, very nice work. The next test is going to be a little bit harder because there's more parts to it. So there's definitely going to be more information on the next test. But I am happy for you all so far. You got a good first grade for most of you. And for those of you who have to take it, no pressure. But you are getting a slightly different version, so I can give everyone back their test. So you're getting a different year. Like every year I make a new test, so you're getting some other year that I gave the exam for. So FYI. Anyway. Next thing is, so we talked about the test. The next thing is looking at structure. I did not put a plus 10% for the pre-ACE packet for anybody. I told you all that I wasn't going to do that until you took both of the tests. I'm assuming it's the second one, but I'm going to put it on because that one's a little bit harder. So I haven't put in, I know about it, I remember it, but I haven't put it in yet. I will put it in after you take the second test, whichever is the lower of the 2 test grades. I'm going to bump up by 10% if you had turned the pre-ACE review packet in on time. Okay, so that I still know about. And then your second exam is actually going to be at the end of this month. The second unit exam will either be right at the end of September or right at the beginning of October. Either the last, like that last Thursday, Friday in September, or the first Monday, Tuesday in October. I mapped it out. That's where we're going to be at in terms of your next test. So you're going to have 2 unit tests before the end of the quarter. You've already done one of them. You have one more, but you also have one other exam before the end of the quarter. You remember what that is? You're going to take quarterly. You're going to take the quarterly about a week before the end of the quarter. And that quarterly is the first time you're going to get an A, B, C, D, E, U level approximation. So based on the amount of marks you got, I'll be able to, give you a good estimate of where you're at right now in the class. And so the test just took, that doesn't give you an A, B, C, D, E, U. That's just, you got a certain amount of marks. But once you've gotten through the amount of material, at the end of the quarter, you take the quarterly, that's a mock exam, and then you get a level. And we'll talk about that as we get closer to it. Still like a month away from now, but I just wanted to give you a heads up that that's where we're at. Labs, they really start in October for us. So starting in October, you're going to get labs, and once you get them, you're going to have titration after titration. Oh, titrations. Did any of you remember those? That's when you had, the really long burette, you had to see the color change. Yeah. So we'll be starting with those next month.
That's what they did.
Oh, yeah. Well, that's what we'll be doing starting next month. Titration. Acid-base reactions. Next month. October. We're not very far away. We just have to finish this unit. All right, so what is Unit 2? Unit 2 is all about compound formation. How do ionic compounds form? How do covalent compounds form? How do compounds interact with each other? And we're going to get into solid, liquid, and gas phases. So we're actually going to do states of matter, but on a molecular level in this unit. So this is a unit that does have a lot of parts. We're on part 2. That's why we had to start. But our goal is to finish in the next 2 to 3 weeks so that we can finish it by the end of September. The quicker we finish, the more labs we get to do when we get into the next unit to stay on track. All right, let's go. Today, we're going to cover something that I would say 75% of it you would have seen in a previous honors class, if you've done all the things that you were supposed to do in the class, and about 25 to 30% of it is new. So just to give you an idea. Next class period, on Wednesday, everything is new. The next class period on Wednesday is the first lesson you're going to have that regardless of if you took previous or not, everything is new in the next lesson. It's called hybridization. It is a weird topic, but an interesting one. So today we're going to cover something called the valence shell electron-pair repulsion theory. Some people call it the VSEPR theory. And I just call it the electrons repel each other theory. Electrons repel each other theory. But this is the fancy theory we're going to go over today. The valence shell electron-pair repulsion theory. Basically, the real lesson is shapes and angles. That's what you'll remember. You'll be like, oh, that's a tetrahedral. That is linear. If you recall those words, that's what we're going into. Remember 180 being a straight line? That's what we're talking about today. And so you have the molecular models in front of you because that has everything to do with the shapes and the angles. And if you'll recall in previous chemistry, for those of you that did have me as a teacher, you probably hated when I told you to memorize bond shapes and bond angles. And I promise you, you're still going to hate it if you hated it before. So it's one of those things, it's basically just one of those, you got to do it or else you don't do it. And if it shows up on the test, you don't get the marks when it comes to shapes and bond angles. But I'll do my best to help you remember, give you techniques to help you memorize shapes and bond angles for molecules using our valence shell electron-pair repulsion theory. Let's go ahead. These are our learning objectives. There's only a couple. Really kind of scary. 3.2. Remember the less objectives, the more intensive each objective is. That's the way you need to understand it. So if you see 10 objectives, now you know that you took that test. For most of you who took it, you're like, oh, it was 10 objectives, but the objectives were really pretty quick and simple. When you see less objectives, it means that the objectives are more intense. Like they're more complicated, there's more to do here, there's more to learn here within this objective. And so the first one is actually a continuation of what we had learned last class. Remember in part 1 when we did dot and cross structures? I told you today we were going to do the more complicated dot and cross structures, that I kept it to simple that day because it was the day before an exam. So we're going to do more complicated dot and cross structures. More complicated. Or what I like to call level 2. Like if it's a little bit more difficult, what could I be looking at? And then 3.3 is explain the shapes and the bond angles using that electron-pair repulsion theory. Using, this is their words, not mine, simple examples such as CO2, CH4, that's the methane that I had you build, NH3, H2O, SF6, PF5. So these are examples such as, that doesn't mean limited to. So you might want to write not limited to. Such as just means these are examples of what you could be asked, but it doesn't mean that that's all you could be asked. Anything that has this structured. All right, so what is a shape and what is a bond angle before we go on? Molecular shape. Is how does it appear three-dimensionally? Like if I were to look at this molecule three-dimensionally, how does it appear? So it's three-dimensional appearance. If the electron cloud models occupied space, what would that space look like? That is what we call the molecular shape. They're like, you know, shapes, like circles, or shapes. It's a shape. What is bond angle? Because believe it or not, every year, both in pre-ACE and ACE, students will not give me a bond angle when I ask for one. They'll give me words. Bond angles are not words. What are bond angles?
Degree angle at which they're bond.
They're degrees. They're numbers, right? It's that's a great term to use. Degrees. So it's the angle around the central element. And so if you have something like this is an example of a molecule, a specific shape. What would the angle between these two outermost atoms be with the central atom in the middle? What would that bond angle be? 180. So when we answer a bond angle, we always answer a number, not words. Be careful here. So bond angle is the angle between the groups that are around the central element. It is literally the same thing as geometry, a geometric angle. The topic, it is what it is. We gotta get through this topic to get the other topics. All right, so this is what we're gonna go over today. We're gonna first start with dot and cross, level 2, then we're gonna get to shapes and bond angles. That's the goals for the day. Next class, we're gonna do something brand new called hybridization. Are we good? Move? Yes? Okay. So I had actually already taught this last class, but just to note, if you have atoms that cannot connect to make an octet with one bond, you have to use a double bond or even a triple bond to do so. And so a double covalent bond is when you have two pairs of electrons shared between two atoms. So you might want to add in shared between specifically two atoms.
Yes.
So this is a double bond. When doing more complicated dot and cross structures, it's oftentimes helpful to do the Lewis structure first and then transfer it into a dot and cross structure afterwards. So we're going to take a look at some more complicated structures today. And so my suggestion is actually going to be to do the Lewis structure first and then to do the dot and cross. So just to take a look, how would we do the Lewis structure for O2? Just to remind yourself, how will we do that? Where do we begin? Go ahead. Two oxygens. That's next to each other. Because there's no other way to put two atoms but next to each other. Then, step 2 is to get a specific type of electron called the valence electron, which we find from the group that the element's in. Oxygen's in group 16, so it has 6 valence electrons. And so, you note here that they do dots and X's. You could do dots and X's, you could do different colored dots, or you could, because it's the same element, it doesn't really matter too much. But let's go ahead and just show one oxygen and the other oxygen. That's step 2. Step 3 is to bond single electrons together until each element feels like it has 8. So if I bond those two singles together, what you're supposed to count is that every covalent bond belongs to both atoms. And every covalent bond counts for how many electrons?
2.
So it's 2 electrons that are shared. Just to remind you of the terminology. So then, at this point, I am currently not done because the oxygen on the left has how many electrons? 7. And the one on the right also has?
7.
And they need to both have?
8.
So we just have to make a bond. And then I had taught you, afterwards you clean it up. And so it looks like this. And how does that look in a dot and cross? Anything that would be in a covalent bond is in an overlapping circle. That's the difference. So anything that would be part of a covalent bond goes inside of the overlapping circle. And so if you've got a double bond, you have to make sure you have 4 electrons inside the overlapping circle. Yes? Yeah. All right. Let's take a look at triple bonds. Same idea. Go ahead.
So for all line bonds, we use dry brackets and draw little covalent bonds in the circles.
Overlapping circles.
Overlapping.
So overlapping circles are only used for covalent. Brackets are used
And
for
they're-
ionic.
They're sharing two because they're close. Because they have
Because the
six
electronegativity is close to each other. They share electrons. Because oxygen can't steal from oxygen. That's the idea, because they both are
Right,
pulling
but
for the
oxygen
electrons.
and fluoride.
They share, they just don't share equal. That's a concept called polarity. Later this week, Friday's lesson.
Yeah, remember polarity.
We will be there.
That's also about electronegativity.
Yes, that all ties in.
I do remember that.
Together.
It was like fluorine is the most, and then it goes all
That
the way.
ties in together. All right, we're gonna continue now. So triple bond, same idea. Nitrogen is the classic example of a triple bond. This is actually how nitrogen naturally exists. You're gonna learn more about this later this year. N2, as you know, is diatomic nitrogen. So like 70% of the air is this molecule right there. Interestingly enough, diatomic nitrogen has very, very strong triple bonds. It is a very, very strong bond. It's also completely nonpolar. We know that nitrogen is generally very unreactive. When we breathe in nitrogen, we do nothing with it. It goes in and goes back out. What is the molecule we do something with?
Carbon dioxide.
Do?
Oxygen.
The oxygen is the one that we do something with, right? We breathe in the oxygen and we convert it
What do you
to
mean?
carbon dioxide with complicated biochemical processes. But we do that. We breathe in oxygen, we breathe out carbon dioxide. We breathe in nitrogen, we breathe out nitrogen. Like, it does nothing. There is no chemical reaction that happens with nitrogen. But it's 70% of our air. By the way, that's why other planets like Mars is 99% nitrogen, uninhabitable, can't breathe. Like, I mean, you could try to breathe, but your body's not going to do anything with it, so you asphyxiate. Why the word species? That was oxygen gas. Anyway, so this is a triple bond, and 3 pairs of electrons are shared, and that's nitrogen. Very, very common molecule everywhere. So let's take a look, and you have this in your homework, actually, just to see what would carbon disulfide look like. What would we do with a key? So I'm going to start with a key. Carbon would be dots or X's.
Dot.
Just make a choice. Sulfur is X's. No right, no wrong answer here. My suggestion would be to draw the Lewis structure and then transfer it. So draw the Lewis structure. So I'm going to draw the Lewis structure. And when I draw the Lewis structure, I'm going to get this. Dot, 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 and then sulfur is and it doesn't really matter how you do it as long as you face the pairs away as much as possible. It doesn't really matter how you do it. But let's see what is happening here. Every carbon and every sulfur has to feel like it has how many electrons? 8. And so if we do this connection, would that be good enough?
No.
About that. Does that complete any of the elements?
Yes.
And so what I used to do is like make a check mark and be like, yep, that one's good. Now, carbon feels like it has how many electrons right now?
6.
And it still needs to feel like it has 8, so it can continue to make regular bonds. And so this carbon's going to connect here. That brings it up to 7, because every regular bond actually adds 1 electron. And then this one has to happen as well. And so you see that your correct answer has to have 2 double bonds. And what that would look like in a dot and cross is how? How would we transfer this to a dot and cross? You could do dot x, so it's x, 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 dot x, dot x. Over here,
Same thing.
dot x, and then
Except
x, x. So once again, my suggestion to help you see what's going on is actually to start with the Lewis structure and transfer it, the more complicated your structure is. If it's not very complicated, you could just start with the dot and cross, to be honest. but the more complicated it is, the more you may want to step back and do the Lewis structure first. Also remember you're allowed to use pencils for graphs and diagrams. Does this count as a diagram on a Cambridge exam?
Yes.
Yes, so because this is a diagram, this is one spot where you would be allowed to use pencil. So you may want to write that. Because remember, for Cambridge exams, you do write them in pen unless it's a graph or diagram. This counts as a diagram. So I highly suggest using pencil if you're doing a dot and cross structure on a paper too. All right, cool. So we've now looked a little bit, and this I had already given you in homework, so this should just be review, hopefully. But now we're going to look at something new that I intentionally did not put in your homework. At least I think I accidentally snuck one in. But if you weren't able to figure it out, I'm not going to count it against you. But we have a situation. There's something else that can happen besides regular single bonds, double bonds, and triple bonds. And this is called a coordinate covalent bond. It has another fancy name called a dative bond. And you should be familiar with both of them. I do believe Cambridge uses dative more often. That's what they use in their textbook. And so what a dative bond or a coordinate covalent bond is if you have a central element that has all the electrons it needs, it already has all 8, but you still have to connect another atom in. If the central element has 8, the only thing we can do is donate. So a dative bond is a donation of 2 electrons for a covalent bond. And what's being shown to you here is this is NH3 that's gaining an H plus to make an ammonium ion. And so nitrogen here already has 1, 2, 4, 6, 8 electrons. But this hydrogen still needs to get on to that compound. It still needs to connect in. So that hydrogen doesn't have an electron to give. And so the nitrogen actually gives both to the hydrogen. And we call that an electron donation, or a dative covalent bond. You're responsible for recognizing when to use both and showing it. In the past, I would have shown it with an arrow, a dative bond. It's an arrow going from the central element to the element that needs the electron. And in this class, where dot and cross structure, it would simply mean that both the electrons would be in your key of whichever element is giving the electrons away. So you have 2 of the same type of electron in the bond. So let's take a look at what that looks like. Draw, this is from the textbook. Remember, checkup means from Cambridge textbook. So from the Cambridge textbook, draw a dot and cross diagram to show the formation of a coordinate bond between the following: H2O and H plus to form H3O plus. You may recognize, maybe not. If not, I'll teach you or remind you. H3O plus is acid. Because H plus attaches to water, and that forms acid. So H3O plus is actually the strongest acid that can form in water. And so let's go ahead and see how we can put this together. It says to use a dot and cross, but it's more complicated, so I'm going to start with a Lewis structure. So I'm going to start with water. Let's start with water. Can we draw the Lewis structure for water? What is the, how do we want to do our dots and crosses? Hydrogen would be, I would do crosses for hydrogen and dots for oxygen. That would be my suggestion. So let's take a look at water. H2O means how many hydrogens and how many oxygens? 2 hydrogens, 1 oxygen. Can hydrogen ever go in the middle? Because it only has 1 electron. So oxygen goes in the middle, and hydrogen goes on the outside. Hydrogen is going to be X's, and oxygen is going to be dots. Remember to face pairs away in single port. So oxygen is 6, hydrogen is 1. And you should notice water is complete with just a single bond to each hydrogen. Do you agree so far? Mm-hmm. Now, what does this say you have to do?
Add a hydrogen.
You have to add hydrogen, but not any hydrogen. You have to add H with a
Positive 1
plus 1. So how do I get this to link into water? You have to describe the process. How do you get that hydrogen to link into water? Because it all needs to be connected.
You share an electron?
Not just one, you actually share
Two.
both. And so what we would do with this is I used to circle them and I would write an arrow like this. And basically the idea is that both of these electrons are making the covalent bond between this oxygen and this hydrogen because this hydrogen doesn't have an electron to share. So both the electrons in the dative bond come from the central element. In this case, oxygen. Whoever has the electrons gives the electron. And so then how would we reflect this in a dot and cross? How would we transfer this into a dot and cross? Start with the oxygen, right? And you've got a hydrogen here, a hydrogen here, and a hydrogen here. So how would we reflect this in a dot and cross? This is a dot and an X, right? This on this side is a dot and an X. On the top, you've got 2 dots for the oxygen. And then what's in this overlapping? 2 dots. And this demonstrates that both electrons are coming from the they're sharing electrons, but oxygen is technically donating its electrons to hydrogen. And that's what we call a dative bond or a coordinate covalent bond. I always like to use this visual idea of what's going on. A regular covalent bond is like a handshake. This is a regular covalent bond. You've reached out, I've reached out, we've met in the middle, right? All right, I am so sorry. A coordinate covalent bond is Rosalind falling off of a cliff and me grabbing her like this and being like, I got you, I got you. That's a coordinate covalent bond. In the end, we're still being connected together, but who's doing all the work? Me. Does that make sense of the difference? Regular covalent bond, we're each donating, but a coordinate covalent bond, one of the atoms is doing all the work to hold them together. Thank you. And hopefully you all get it from that scary display. We're good so far? I saved her. I saved your life today. You saved me. Just remember that. All right, are we good to move on? Try it again. This time for NH4+. See if you can draw the structure for NH4+. Dot and cross. NH4+. Now, this is a polyatomic ion, isn't it? Oh no. Words. Scary words. Polyatomic ion. Put brackets around that. When you see a polyatomic ion, do we cry? Like it's choose a direction. Put brackets around the NH4. What type of positive is that? +1, +2?
Positive.
Yes. Okay. So we're going to breathe in and breathe out, and we're not going to cry yet.
Yeah.
It's ammonia. If I were to draw the Lewis structure for ammonium, do you remember what to do if you had a polyatomic ion? +1 means to do what? Give an electron or take away?
Take away.
Which element would I take away an electron from?
Nitrogen.
All right, let's revisit that. So let's first start, and remember pencil, right? We do pencil for this, not pen. So I haven't answered if anybody's right or wrong yet. I'm just gonna write this. Remember step 1 is that, right? Step 2 is what?
Draw the valence electron.
Valence electron, right? So keep P is gonna be, I'm gonna do nitrogen is dots and hydrogen is X's. That's what I'm gonna do. So nitrogen gets how many dots?
5.
5. And hydrogen each gets 1 X. Alright, here's where the decision is. This is the decision that you have to make. Make it correctly. There's a +1 charge. +1 means take away electron. Which element, and yes, it goes back to electronegativity, it's the elephant in the room. Which element is most likely to lose an electron between nitrogen and hydrogen? I'm going to bring up that F, O, and N are the most electronegative elements,
Oh, so the least electronegative would be the one that is taken away?
which means they want electrons.
Okay.
The least electronegative element is the one most like a metal. And which of these would be most like a metal, even though it's not a metal? Because remember, it gets a +1 charge, generally speaking. It's hydrogen. It's hydrogen. Hydrogen loses the electron. So hydrogen, so make that note. I left it blank on purpose because we had to answer that. You have to make that decision. It's from hydrogen. You can always remember hydrogen loses the electron if it's with a non-metal. It always does. This is the less electronegative. So pick one of those hydrogens to erase an electron from. Which one? Pick the top. Makes sense, right? Pick the top one because it's the only one that has a pair on nitrogen, right? So pick the top one to kick out an electron. Goodbye. Where did that electron go, y'all? Some other anion took it, like a chlorine or fluorine. It went somewhere. Not here anymore. Bye-bye. Electron gone. So what do we do next? Step 2 is the hard one for polyatomic ion because you had to figure out who to take the electron away from. It's going to be hydrogen. And then now step 3 is pair, pair, pair. And how do we connect that last one in?
Donate to electrons.
Donation. Which is why I usually circle them and write an arrow. Now, how do I transfer this to a dot and cross? Oh, like this. No, I don't want this over that. H, 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 right? Dot X, dot X, dot X, and up here, dot, dot. And that is your evidence that this is a coordinate covalent bond or an electron donation taking place. So this is the electron donation. All right. Here. You did it. This is not the most complicated dot cross structure that exists. Next class, I will show you the most complicated one that exists. That you have to know for the future exam. Yeah. Next class. I already showed this. I don't know why I accidentally repeated it. This has already been done. So we're moving on to the second part of today. VSEPR theory. VSEPR theory. All right. Or what I call the electrons repel each other theory. This fancy term stands for valence shell electrons. The pairs repel. So valence shell electrons, valence shell electrons, pairs repel. What do we mean by that? Well, we're talking about molecules now. We're out of atoms, right? We're out of atoms, we're out of singular atoms and ions. We're now talking about molecules and how molecules connect. So you've got your good old CH4 in front of you, right? If I have, let's use carbon dioxide. Because you did this as a homework. You drew carbon dioxide and you should have gotten something like this, where the oxygens were apart from each other like this. Or you got this. One of these is correct and one of these is incorrect. Which one's correct? Which one's incorrect?
See, the first one's correct.
So this is correct. And this is incorrect. Okay, what's the issue? What's the problem? What's going on with that? Why is this not a way we would ever write carbon dioxide? Go ahead.
Because the electrons can separate even more.
So the idea about electrons is they repel each other. So the idea is that electrons would like to be as far apart from each other as possible. So if you imagine this as negatives, right? Negative, 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 negative. And you imagine this as negative, 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 negative. Your option is to have all your negatives like that, or to have them spaced farther apart. And which do you think is more appropriate? Space electrons as far apart three-dimensional as possible. So that's the idea of valence shell electron pair repulsion theory, is that molecules will orient themselves naturally. This just happens in such a way that the electrons are going to be as far apart from each other as possible to minimize the repulsive forces. Yes. There you go. The space electrons as far apart away as possible. And because electrons naturally space themselves as far away apart from each other as possible in groups of atoms, this is what gives us all of our shape predictions and all of our bond angle predictions. So if you hold on to that idea, it will help you to reason why the answers are what they are as we go through the different shapes and bond angles you're simply going to have. Nice. All right, so let me know when you're good to go. I pulled up and I posted on the class stream a simulation that I do with the pre-ACE class that I'm going to show you a little bit now. And so I'm going to show you a simulation first on PHET. It's good for a visual, especially, I don't know how many of you are like me. I am terrible thinking three-dimensionally. Some of you are artists and can think wonderfully three-dimensionally. Not great at it myself. I'm a two-dimensional algebraic thinker. Like, I can solve problems, but spatial reasoning is not my strong suit. So things like this are very helpful for me. If we take a look at model, and so we're going to take a look at this is the simplest type of, pretty much the simplest type of molecule you could have. You have a central atom and you have two atoms around it. So every one of these spheres represents an atom. And so this is something very like BEF2. BEF2 would be an example of something that looks like this. If you toggle the molecule geometry and you turn that on, it tells you the name. The name of this is linear. And if you show the bond angles, that it tells you the bond angles are 180. And we can kind of like manipulate this around and try to move them closer to each other, but the molecule naturally goes back to 180. And so if you add in another atom, let's say we added in a third atom to go around the central atom, what do you predict would happen? Where would you want to put it? Would it go 90 degrees here? What would happen if I were to add the third atom? Go ahead, Alex.
The other atoms will separate.
He would separate more, right? And so let's do it. And he would separate to become 120, right? So this is 3. So our geometry changes to trigonal planar. Literally, if you draw it, it's a triangle. If you draw the edges of it, it's a triangle. Why is it called planar? That word planar, go ahead. Because it's flat. Planar actually means, and we'll go over that in a little bit, it means two-dimensional, not three-dimensional. And so it's a flat triangle. And so what happens, and let's look at your methane, if we added one more? Put your methane back together. What would happen if you added one more? What would the bond angles be? If you look in front of you, are they 90? Let's see. They shouldn't be. What happens? The last group does what? And let me borrow yours. It makes an angle, and if you hold your hand flat to two of the groups, you should notice something. So do this now. Hold your hand flat to two of the groups. Only two of them will ever be planar. One group will face away from you, and the other group will face towards you. So instead of being a two-dimensional molecule, once you get to 4 atoms around your central element, you move from 2 dimensions to 3 dimensions. That's complicated, because now you have to think 3-dimensionally. And that's what these little model kits help you out with. And so the moral of the story is that when you have 4 groups, you don't have 90-degree angles, you have 109.5. And are you going to have to memorize those angles?
Yes.
You betcha. Unfortunately, you will have to memorize the geometry, and you'll have to memorize the bond angles. And so this little simulation, which I have posted, and I posted it, it includes real molecules as well if you want to see, like CO2, here's CO2. We can predict by looking at this what the shape and bond angle is, right? It's a straight line. What do you think the name of it is? Linear. And the bond angle is what you think.
180.
180. Right? CO2? Only logic. Let's take a look at another one.
The reason that it's true is because it has 2 instead of 1 connection per atom. Because,
No.
for example,
I mean,
H2O was like, is it because
that we have to get to. So take a look
only
at
has
H2O.
one, right? Is that why they're not?
This is H2O. If you take your methane, right, and you take, let me borrow your methane? 2 of the groups off. Those stand for lone pairs. Instead of atoms, those are pairs of electrons that are lone pairs. That's not linear. That's what shape. This is the same thing as water, and water is simply vectors. And so what you're going to have to recognize is that if you remove the atoms, but you still have the electron groups, it still retains that tetrahedral shape, but you don't have those atoms anymore. So it ends up looking like it's like a V or bent or an angular shape. And so going back to our actual lesson, here's what you're going to have to do. And I think I might give you a paper to help with creating more of this. You are going to have to be able to draw the Lewis structure. And once you draw the Lewis structure, we're not going to do dot cross. Only do dot cross when you are implicitly told dot cross. Otherwise, Lewis structure. So draw the Lewis structure, and you're going to count the groups of electrons. Now, what do I mean by groups of electrons? That means side of the central element that has an electron coming out. Then you're going to have to figure out how many of those groups are bonding pairs and how many of those groups are lone pairs of electrons. And that's enough information to predict the shape and the bond angle for any molecule. And so there's specific shapes and bond angles you're going to need to be familiar with and I'm going to go over those, and then we'll recreate them on some paper. All right, so first things first, count the total number of groups of electrons, count whether they're bonding pairs or lone pairs, and then you're going to have to memorize some information. Ready? No? See if I can pass something out while I'm holding. Hold on to this. Look, it matches your softball. Hold on to this.
Oh. Down.
All right. Yes. Muy Lina comes up. All right, here we go. So don't write on the cardstock yet. You'll be instructed on what to do with it momentarily, because I'm gonna try to make the information a little bit simpler. We'll use the graph in the front. So here's the deal. The bad news is you are gonna have to memorize how many electron groups, how many lone pairs, what's the name of the shape, and what is the bond angle. Some of it is hopefully apparent, like linear. Some of it is not quite so apparent. And so, not only do you have to know the electron groups, the name, the molecular geometry, you also have to be able to write the 3D structure appropriately. And so I did actually teach you this back in pre-ACE. Definitely if you were in last year's group, we did wedges and we did dashes to tell us if we had something coming to us or going away. I'm going to reteach that now. But it is something you've hopefully seen before. 2 electron groups, you only got one choice. 2 electron groups means that 2 sides of your central element have electrons coming out. You've literally only got one choice. It is linear. 3 groups, you kind of have 2 choices, but you're pretty much only going to see one of them usually, and that's trigonal planar. However, if you had 1 lone pair and 2 bonded pairs, that would be the same name as water, which is bent, but the bond angle would be different. And there's something you need to write here. Every lone pair, you subtract 2 degrees from the main, subtract 2 degrees from the main bond angle. What does that mean? This would be considered 118 for Cambridge. If there's a lone pair, you subtract 2 from the main group.
Why does
For water, it would be minus 109.5 minus 2 is around 107. And then for water, it would be 105 because you subtract 2 twice for 2 lone pairs. So this would be 107.5. And this would be 105.5. So you should write that down. 4 and 1, 107.5, you subtract 2 degrees. For water, which has 2 lone pairs, it's about
there's some that have
105.5.
like two sets of degrees, whatever those are.
We'll get there. Lucky and unlucky for you. You should also put approximate here. Because actually, depending on the groups, it's slightly different. Depending on the electronegativity and the size of the atoms that are around, this could be somewhere around 106.5 to 107.5 actually, and this could be somewhere from 104.5 to 105.5. But the idea that Cambridge is going to ask you to remember is that every lone pair repels a little bit extra, 2 degrees around, from the main. And so you just need to memorize it says less than 109.5 here, but you should just remember it as 107. and you should just remember this is 105 instead of less than 109.5. Cambridge won't accept less than 109.5, so just so you're aware.
For the, take the same for
So,
the two pair ones? The two number ones?
don't just write less than 109.5 here, write 105. Now, something to bring up. Take a look at your methane again. Top off one of the atoms. Top off. What is that new shape? Is that planar or net? Does it lie flat or net? Not quite. Not quite. So if you pop off one and instead put an unshared pair, that actually gives you the pyramid shape. This is shaped like a pyramid. Each of the sides are going down. And if you pop off a second one, you get what shape?
Bent.
Bent. You get this shape. And so you can actually look at methane to predict the others. All right, so what about what's going on the next slide? Because this is what we did. This is a first year, by the way. First year honors pre-ACE Chem, you should have memorized these. If you didn't, oh well. You're gonna memorize them now anyways. This is what's new. So, yes. This is what's new, and before you freak out, I have good news for you. If you look at the objectives from Cambridge, a lot of these you actually don't need to know. If you were to take a college level chemistry class at the local university, you would need to know all of them. But for Cambridge International, you don't need to know seesaw. You can cross that out. You don't need to know C structure. Cross that out. I've never seen them test linear, so you can cross that out. It's not in the objective. I will keep one extra one here that I have seen them test. And you can cross out square pyramidal. So out of the 7 here, I crossed out how many? 4. You're welcome. So there's 3 of them that are left that you do have to know, that I would suggest. 2 of them that are in the standard, and another one I've seen on questions before. So I want to make sure that I've seen it in the textbook, and I've seen it, even though they don't explicitly outline it, I would know this last one. So 5 and 0, meaning 5 groups. You just have to memorize that it's always, if there are 5 groups like PCl5, this is like if you have 5 atoms around your central atom, which is those weird scenarios we learned last week, always called trigonal bipyramidal. Now it's kind of really cool if you can visualize it. So it's trigonal bipyramidal. You do have to memorize the angles are 90 and 120. If we go back to the PHET, which you can play around with when you have the time, but let's take a look at one that has this, PCl5, okay? Because I'm not really, like I said, I'm not really the most visual person, but if you can organize this correctly, you can actually see what's going on here. This is called trigonal bipyramidal. Why? If you look this way and you cross lines here, this is a pyramid. On the bottom, there's also another pyramid. So bipyramidal means 2 pyramids. And so you can see that the base of the pyramid is actually these lines here. That's the base of the pyramid, and this is supposed to be the top pyramid, and this is supposed to be the bottom pyramid. And so you see here that all the angles are 90 degrees. If I were to flip it to what you see here, here, there, and there, the angles there are going to be flip it to the other side. It should show me the 120. Yeah, they're there. So if I flip it the other way, you see the 120s? And you can also see here, this is looking at the pyramid from the top actually. And so these form, the 120s form the base of the pyramid. So you may want to take a look like that if you are a visual learner. It helps. Otherwise, you can just remember it as pyramid at the top, pyramid at the bottom. That's why they call it trigonal bipyramidal. Also, it's more complicated, so instead of one pyramid, it's two. And the angles you need to memorize are 90 and 120. The 120s are the 3 here, and then the 90s are the 4. Which ones are we skipping? We're skipping seesaw, we're skipping T, we're skipping linear. Octahedral is the next one you need to know. 6 and 0 is octahedral. I apologize because the prefix doesn't sound right. If you think about it, 6, prefix oct stands for 8. Well, what do they mean by octahedral?
Because there's 8, 9.
There's 8 faces. And so if you look it up, and so again, it might help to kind of look it up. Octahedron. This is just to help you get some understanding. This is what it looks like. It has 8 faces. You're to pull up what an octahedron is. It's that. That's an octahedron. Oh, that's another one. That's an octahedron. Another way of looking at it is here. That's an octahedron. And if we go back to here, and we go look at this, it actually forms, if you look at it, it forms the top thing, and it forms the bottom thing. So there's 8 faces there. So that's why it's called an octahedron. And if you can't remember that, then you just remember 6 and 0 octahedron, or octahedral, the end. Like it's something you just gotta know. But if you can visualize it, it is because it has 8 faces, the shape of it. So some of you, like I said, are gonna be better at that than others. I'm actually terrible at it, so I just straight up memorized it. Like I'm terrible at visualizing it. After looking at the images, I get it, but I just memorized the words. That's how I've done it. All right, so we need to know trigonal bipyramidal. We need to know octahedral, right? Supposed to be dral. All the angles in octahedral are 90, by the way, so that's easy to remember. And then the trigonal pyramidal is 90 and 120. The final one that I would suggest you know is square planar because I've seen Cambridge test it. There's a very specific molecule that has this structure. I'm going to write out exactly what it is, exactly what I've seen tested. XEF4 has that exact structure. And basically, it's 6 groups, but there's 2 unshared pairs of electrons, and all the other groups are lying 90 degrees apart, so like a flat. That's why it's called a square plane, because it's literally a flat square, is the shape it makes. And so all the angles here are 90, all the angles here are 90, and then here is 90 and 120. That's what you need to remember. All right, so that's straight up what you need to do. There's a little bit more, though. And so I did write down the steps. Steps to determine the shape and bonding of a molecule. Step 1, draw the Lewis structure or the dot and cross if you fancy pain. I did write that. If you don't fancy pain, then, you know, Lewis structure. Count the bonded groups on each side, count the unshared pairs, and then you're going to have to consult the memorized molecular geometry chart. Now before we do that, let's do one more thing. We've got time. I gave you a cardstock on purpose. So what we're going to do with that cardstock is we're going to add in some things you absolutely need to know. This is shapes and bond angles for just the groups you need. Shapes and bond angles. So what I would like you to do, you can use either a pen, I do not suggest pencil, or you can get a Sharpie. I have Sharpies for everyone to borrow. Yeah, pen or Sharpie. Pen or Sharpie. Pen or Sharpie. Pen or Sharpie.
on your own paper.
Yeah.
You ruined my whole paper.
She let me have it. She let me have it.
Bro, they did.
Yeah.
Just give him, if I let you borrow it, just give it back to me at the end of class. Okay. So, you're going to create this so that you can work off of it. Not only do you have to know the shapes and the bond angles, you may be, and quite possibly will be, asked to write the three-dimensional structure, which I have not yet addressed. And so, what we're going to do is write the bonded groups, the lone pairs, the 3D shape, the name of shape, name of said shape, and finally the bond angle. So the way you need to know it for Cambridge. We could even do polar, non-polar if we wanted to be spicy.
Oh.
Oh yeah, 'cause you might want to leave yourself a column for polar, non-polar later on this week, because you can actually look at the shape and determine polarity like that for many atoms.
That's crazy.
So maybe leave yourself some space for polarity. Not today though. We're not doing polarity today. All right. So first one. 2 bonded groups, 0 lone pairs. What does that 3D shape look like? Just element in the middle and elements on the outside. I'm going to use the letters X and Z. Why wouldn't I use Y?
Why is an actual element?
Y has an actual element. So I'm just going to use X and Z because there's no element Z and there's no element X. Okay? That's the reason why I'm choosing those. So X and Z. All right. If I have 3 atoms, literally straight line. Straight line. What is the name of that shape?
Linear.
Linear. And you've got to memorize that. And what is the bond angle?
180.
180. So that's the first one you got to know. Easiest one. The next one that you got to know. 3 and 0. The 3D shape for this is always this, this. And if they ask you for the 3D shape, you have to angle your groups apart. So you have to write it like this, so that it makes what looks like a triangle. If you were to connect the outer edges, it would look like a triangle. This is the 3D shape. So far, so good? What's that name of that shape? It's trigonal. It lies flat, so it's called trigonal.
Pyramidal.
Not pyramid, but planar. Because it lies flat. And the bond angle here is always 120. And where is that bond angle? Just to be clear, it's between any of these 2 groups around the central element. That's 120. That's what I'm writing the arrows for, just to point out that that's what the bond angle is. It's between those 2 groups, or these 2 groups, or those 2. They're all the same, 120. 120 plus 120 plus 120 is 360. That's the reason why that ends up to 360. 2-dimensional. All right. The next one you have to know for Cambridge that was in the standards. 4 and 0. You've got 4 bonded groups. You've got 0 lone pairs. It looks like this. X, B, Z. Okay, this is where it changes. Wedge. Yeah. And dash. You remember what that means? Right here. What does a wedge and a dash mean?
It's what they're writing.
So wedge says coming towards. It's facing towards you. And dash means behind or facing away. So look at your methane again. If you look at your methane and you hold your two groups up, you're going to notice that one hydrogen atom is going away from you and one hydrogen atom is going towards you. You see that? The one that's going towards you would be what? A wedge. And the one that's going away from you would be a dash. That's how you three-dimensionally have to write it for Cambridge, because you don't get to build molecules on a Cambridge exam. You have to write it on a paper. Yes? So then, what's the name of that? It's got 4. Tetrahedral. It's three-dimensional, which is where hedral comes from. Anything that's three-dimensional gets the hedral term. So it's tetrahedral. And the number that we got to memorize is? 109. The next one you got to know is 4 and 1. 4 and 1 is this. And trying to make it straight. You replace one of the groups with an unshared pair of electrons. So you get one angling down this way, one angling down towards you, and one angling down away from you. You have to imagine that that's called a, if it's 3 going down, it's a pyramid, right? If it's 3 facing down, I'm trying to do with 2 hands, but if it's 3 faces facing down, it's a pyramid. And so this is what we call a pyramid. It looks like this. We can also call it, it has 2 possible names you can give it. Both are okay. If you want to write less, you just say pyramidal. That's the right less. Or you can say trigonal pyramidal. You can say either. You can just say pyramidal here, and that's okay. Cambridge accepts that. Or you can say trigonal pyramidal. Either of those are okay. So pyramidal. Yes. As soon as this is out of pyramidal. And the number we need to know here is 107. 107, 107.5, that area. The next one is, go ahead. 107.5, they accept either. So it's a little bit of a range, and the reason why is because it depends on the size and the electronegativity of these atoms. So that's why it's a range. -2 or -2.5. They accept both of those. All right, next one, 4 and 2. This is, take another one of these and you snap it off for an unshared pair of electrons. It's still 4 total groups, but only 2 of those groups are atoms, and 2 of those groups are, next Rebecca, are lone pairs. So you get this. And this is the one that gets confused with linear. It's not linear, it's, if those unshared pairs of electrons are there, it's actually called bent. This is the shape of water. And the bond angle here is approximately 105. Remember, you subtract 2 for every unshared pair from the main amount, which is 109.5. Yes. You can go next, yes. Yeah. I need more space, right? How are we doing? You okay so far? No. All right, we've got a few more to do. I'm going to save this and add another slide. I'm going to keep this, add another slide. So we said it was bonded groups, lone pairs, 3D shape, name, and bonding. All right. So I've never seen them ask for the 3D shape for 5 or 6, by the way. I've only seen it for 2, 3, and 4. Because for 2, 3, and 4, you really need to know it for organic chemistry anyway, so I think that's why they asked for it for 2, 3, and 4 groups. So let's talk about what we need to know for 5 and 6. So the bonded groups, 5, lone pairs, 0, 3D shape, you would just need to recognize that you've got 4 groups, so we're going to do X and Z again. 4 groups that are 90 degrees. And then the last group would be somewhere like this, 120 degrees. So it's got to be 3 120s and 4 90s this way. 90 and 120. And the name of this is called trigonal bipyramidal. So you've got to memorize the name. Trigonal bipyramidal. How often do 5 and 6 show up? Actually, not really that often. 5 and 6 don't show up that often, but you should know them anyways. 6, 0. 3D shape for octahedral. What would that look like? All 90s. So we know it's going to be, it's actually like this. X, and then B, 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 and then the idea being that 2 groups are coming at you, 2 groups are going behind, and then these are 180. So they're all 90 and 180 degrees. This is called octahedral. And 90 degrees is the bond angle you need. All the groups are pretty much 90 degrees apart from each other here in octahedral. So for 5 and 6, I wouldn't stress too much about memorizing the 3D shape, but for 2, 3, and 4, absolutely. You have to know linear, you have to know planar, and you have to know tetrahedral off the top of your head. If they ask you to draw the 3D shape for those, you have to do it. For these, I would know how to count them and what their names and their bond angles are. Did you leave yourself for polarity? Leave yourself some space for polarity? Believe it or not, the topic we do next class, which is hybridization, we could actually put another line for that as well. If you have space. If you don't, we'll address it next class. So you can actually look at the Lewis structure and figure out a whole lot. Just by counting how many groups of electrons are around an atom, you're going to figure out a lot about a molecule. How, if it's polar or non-polar, how it hybridizes, a lot of stuff. Today we're doing shapes and bond angles with it. So, most of what we're going to see for the rest of the class is just practice examples. I wanted to start with this so that you have it to look back at as we go through practice examples. So I'm going to save this. Let's get to practice questions. You're going to see how quick it is. Predict the shapes and bond angles for CCl4. So that means your correct answer will be a shape, a name of the shape, and a bond angle. I would go one step further, and I would also give one more piece of information. I would give the 3D shape. This is something that I do see commonly asked on Cambridge exams, so I think you should practice it. So give the 3D shape. 3D. Oh. So 3D shape diagram is what I mean. So how do we start? What should we do first? Steps are draw the Lewis structure. Yes? So start by drawing the Lewis structure. Most of these I've given hopefully are not too stressful. So I'm going to start with the Lewis. What does that look like here? CCl4. What goes in the middle? Carbon. And what goes around? And what's next? Valence electron. Carbon gets 4, chlorine gets 4. That's step 2. Next step. Singles gotta mingle. Singles gotta mingle. You put your single electrons together, you get this. This is my Lewis structure. From this, I can predict a lot. First, what's the name of the shape? That. How do we figure that out?
The groups
Count your groups.
and the bonding pairs, the pairs.
So count total groups. You want to do it that way? How many total groups of electrons are around carbon?
4.
4. How many of those are unshared pairs?
None.
So lone pairs, 0. Use your chart. Tell you what this is. What is it? Tetrahedral. Which makes sense, 4, right? Tetrahedral. That's what you gotta memorize. What's the bond angle?
1 and 9.5.
And if we were asked to draw the 3D structure, how would we do it? C in the middle. Put Cl at the top. Cl like that. Cl like this and Cl like that. When giving the 3D shape, you do not have to give all of the correct valence electrons. You're just giving the actual shape of the molecule. It's a tetrahedral structure. It's a little bit different than the Lewis structure. But this would be the 3D shape. Are we okay with this idea? Shows me one chlorine coming at me, another chlorine is going back. Why am I stressing this right now, even though they didn't really say to do the 3D diagrams? First of all, I've seen it on a lot of old Cambridge exams, number 1. Number 2, when we get to organic chemistry, this is a thing. Like, being able to draw our molecules like this is a thing. So you want to practice it now before we need it later on. Yes? December. Probably, I mean, depending on time frame, probably the week we come back from Thanksgiving is usually when we start organic chemistry. So, end of November, probably. That's where organic chemistry begins. So there's a reason behind me teaching this now. A couple of reasons. I have reasons. Let's take a look at another one. Same thing. We want the shape, we want the bond angle, and let's do that 3D structure. So shape, bond angle, 3D structure. Shape, bond angle, 3D structure. I'm just going to write it like this. Oh, good old beryllium. Remember that beryllium is okay with having less than 8. If you'll recall from last week, we said it was an exception to the octet rule. It could actually get by with having 4 valence electrons, which is what's going to happen here. So what's the Lewis structure for beryllium chloride? Start with Be. Valence electrons for beryllium?
4.
2. Right? It's going to end up with 4, but it only has 2. Valence electrons for chlorine? 7. And if you need a reminder, it's from the group, and you just take 1 away from the front of the group. Now what? That and that, right? Shape.
Oh.
Straight line, right? Linear. Bond angle. 180. 3D structure.
X is 2, B.
You gotta put the actual, like, what it is, but, like, still a straight line. It was a straight line, it's still a straight line. Like, there's nothing fancy here in the 3D structure for beryllium chloride. There's no, it's 2-dimensional. So there's no wedges, there's no dashes. It's quite simple. We probably wouldn't ask you for a 3D structure. So usually do for tetrahedral. All right, start with it. Go textbook questions. Not this one. So same question, shape.
So it would be big groups with 0, 1.
Bond angle. And this one we do want to be careful with. Shape bond angle, I might need to correct this a little bit because this is actually total groups. Change bonded groups in your to total groups. Change bonded groups to total groups because this should say total groups. Because that only makes sense for 4, 0, 4, 1, 4, 2. If it's 4 total groups and 1 lone pair. Change bonded to total. Yeah, change that to total groups. That'll make more sense. Use a Sharpie. Yeah, change that to total groups because that'll make more sense. As we do this. So, phosphorus chloride, what's that? P. How many chlorines? 3. Valence electrons for phosphorus, how many? Phosphorus, look at group 15, so it should be 5. 1, 2, 3, 4, 5. Chlorine is?
7.
I just wanted to do that like this. Quicker. That's this. I don't have my iPad. All right. Now what? This connects, and that connects, right? So how many total groups are here?
3. Actually, 4.
Total groups
4.
counts everything. You have to count basically the sides that have electrons coming out. It's 1, 2, 3, and 4. So when counting total groups, you count all the bonds and you count all the lone pairs of electrons. So we've got 4. How many of those are lone pairs? So 4 total groups. How many are lone pairs?
1.
1 lone pair. So what's the name of that shape? That means that these electrons basically bend these chlorines down. So that's why it looks like a pyramid. And so it's called pyramidal. The bond angle is then approximately, you can't say 109.5 anymore. You've got to subtract 2.
So it's
Degrees.
107.
107.5 or 107.5.
Let's see.
So every time you have an unshared pair of electrons, you subtract 2 degrees from the main group. The main group for 4 is 109.5. So you would answer 107 or 107.5 here. Like I said, for the ones with lone pairs, there's a range of answers they do accept. All right. And finally, how would I draw the 3D model?
So you would have one little triangle. What's that called?
You have the P, and then
it would connect to one CL just normally to the side. Then one would go forward, and then one would go backwards.
like that. That's how it looks.
Oh, the 2 points on top.
All the atoms facing down, like a pyramid. Yes? What does that look like? You take this off, there's your pyramid.
Crazy.
All right, continue. Should be. Just practice questions. Okay. 1, 2, 3, 4. I think. Yeah, is it there?
Yeah, there is.
What time is it? It's about 2. So guess what? I think there's 4 practice questions here, and you can do some of these. So I've pushed you through a bunch. See if you can try these using the same method. Raise your hand if you've got it, or you think you've got it, and I'll check it off as you go along. Binder check, by the way. I know I didn't check your binders in the first test because there wasn't very much to check. For the second unit test, I will be checking your binders, meaning all your notes from Unit 1 and Unit 2. I'm only going to check once a quarter, so all your notes from Unit 1 and Unit 2, I'm going to check on the binder check for the Unit 2 exam. So start putting your binders together or your folders together if you haven't already. You do need to keep your notes throughout the class because You need to study for the end of your exam, so you need to keep all your notes for this class. All right, so once again, for those notes, I'll be checking off when you get questions right. So check each of these. Do the last 4 the same way that I did the first few. Yeah, that's it. Yeah, that one. If you want me to check each one as you go along, that's fine. Or you can wait for me to check once you've finished all 4 and I'll tell you what you got right and what you got wrong. I do advise pencil, but if you want to use pen, you may have to scratch out and write somewhere else. You don't get it right. You graduated 10. You already graduated 10.
That's where I'm
Just to be clear, if for the last 3 you only need to give the shape and bond angle, you don't have to give the 3-dimensional diagram for 5 and 6 years. So only need to give the 3-dimensional diagram for hydrogen sulfide. Just give me the shape and bond angle for the last 3.
Yeah.
Once you're ready for me to check off, let me know. What? Yep. It is.
Oh, it's this one.
I just said that.
It's gonna take one of its electrons, like it has 8, right? So it's gonna take 4 of them and connect them to 4. So there's gonna be 4 of them left that don't connect. So it's gonna end up being.
I said
I believe you.
I also did.
It would like that. And then the idea is you write a fluorine there, fluorine there, fluorine there.
Okay.
No, that's
That would actually give you,
It is like that.
it would give you the structure.
No.
Fluorine there, fluorine there, fluorine there, fluorine there, fluorine here, fluorine here.
Yeah, but
Whatever.
I gotta shut up.
What are you doing, bro? You have it right here, always on.
I can do that.
Square planar. That's the one that I mentioned in the notes that there would be one specific example that they bring up that is square planar. It is XEF4. That's the only one that I've seen tested ever. But if you had like XeCl4, XeI4, like any design with that xenon with a halogen, yes. Yes? You gotta bend it. Oh yeah, you gotta bend it.
I didn't get the right
Yeah.
Yeah.
For the back, you don't have to do the 3D structure. You just have to measure the shape and the body. Perfect. You just have to give the names of the shapes and the bonding groups. What's the name of the shapes and the bonding groups? All right, I'm passing out the homework. Once you're done with the in-class questions, you can just tell me you turned it online. When you're done, pass it forward.
No, I imagine I'm doing it because I can't see that.
I'm one step ahead.
Pass your homework. You've got about 15 minutes. You can either do it or take a break. It on the other page. I did mention it by formula.
It's online day school.
XEF4.
There you go.
XEF.
Has any of you watched The Office? I have a reason for asking. Because every time I see this, I think negative. You actually did it, but like, you can't walk by and not think of Megadeth. I don't know. What are you saying?
Oh, my bad. I mean, it's up for you. I don't know. I mean, maybe
And I gave you the homework.
Oh.
Yes. Oh yeah, let me give you your tests back. I'm still checking, but I will be walking around and give you your tests. They are in no specific order. Am I entering?
Because I get that it's this, but not that.
These are good. And then the other side? All right, as I give back your test, you need to hold on to these. Do not lose your test. I'm giving them back to you to keep. Use them to study for quarterly. Use them to study for the end of year, paper 1 and paper 2 exams. Just hold on to them. These are given out in no specific order. I didn't grade them in any specific order either. I just graded them as I saw them. Rosalind? So, your test. Steven? Alex? Mary? Mike?
I read until I. Yes, I know they should.
Life is hard. But it's okay. It did. So how was that? And that was ionization energy. It's 3 marks.
Look, guys, I got 24 out of 28. But like 24, like 24 is such an odd, like such an even number. Just feels too right. So I would say I'm more of a 25 out of 28. But like 25 out of 8 is like an odd number. I don't like odd numbers. So like, and the square root is 5. So I don't like getting a 5 out of 28. So I'm like, okay, that's 26. But like everybody knows 26 is just the same as 27. So I really have 27. Now, 27 out of 28, come on. Just give the whole point to me. So I have 20 out of 28. But on that one, what is it going to change if I get the 10? I have, so basically I have 110.
Yeah, but
I
So like, technically, David, I got all of this stuff. All of it.
that one. You get your definition.
Okay, the production work
Your
is
definition, yeah. I know I got it wrong. What is it? Oh, actually.
Hear me out. I have an explanation for how you do this behavior. This is not the correct behavior.
You still go.
With zero.
Keep it.
Yes. It
So you would do 2 out. Yeah. Oh, okay.
Everybody needs to look over the exam. Even if you got an A, there's still feedback. Even if you got an A. Yeah. Nobody got a perfect score.
How would you guys do it?
So check.
Just like that. That's a
90 and 120.
That's a 3D shape. I want the Lewis structure. It's still the same thing.
Still working on this question.
Yeah.
So I just wanted to bring up, everybody did well, but still look over your test. There's feedback for everyone.
I was gonna put one else, then I'm like, no.
Did you write your name? Did I miss it? Oh, you forgot to write your name. No, I believe. I remember you being there. Yeah, I checked this though, so make sure next time you do. I will correct it. I'll put it in right now.
Thank you. Just so I can.
Yes.
Just so we can go in.
Yes, the credit for the binder check. When I check the binder, I'm just checking that I've signed off.
Right.
So this is good too. Yeah.
Okay. Thank you.
Hakeem, it's updated. You're welcome. Question? All right, who still needs me to sign off for your final questions for today's lesson? 3, 4.
Oh yeah, I forgot. Give me. Yeah, so I have a little mathematics problem for you right here. Well,
You tied for the highest growth score.
I also have mine. So here is how many problems do I
No
have?
33. But no big deal.
Good.
33 is
Now,
now you can see how the growth is there. That's by mark. You still have to burn mark,
so look here.
but
There's
it-
this thing right
cuts off.
here. One public, right? Then there's this other public. But then there's also this public here. And then there's this other public. So tell me in which one is yours? Sure.
It's square meter, because there should be a shape.
It's just you didn't take down. You want to take a picture of mine?
Oh yeah, you can take a picture.
Yeah, and I got one.
This is correct. You just have to-
I did that line, but I just put on bigger.
Oh my god, my son is too sweet.
You're the second.
I put the biggest one.
Basically.
I've never been called this a P-word, but today
I
I'm
got
called
these
this.
two
I don't know if both
I
sides.
got all of this right.
No.
But today I was called this twice.
Now hear me out.
Double check.
Hear me out. It's one of these.
Oh, yeah.
There's this.
Yeah, I got these.
This.
Oh,
There's this.
this one?
Yeah, I
So,
So H3 plus,
this.
right?
No.
H3
No, 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 no. This.
This
This. This.
right.
Right.
They each have. That's why it's all of them have zero neutrons. So that's 0 to 0. It's a total mark. And then the full ion, because the polyatomic ion only uses 1.
Hey, yo. Just right here.
Yeah. How may I help?
Oh, okay, David.
I'm 6 now.
I mean, there's this one too.
Like right now? I got
Tomorrow.
and I got
Tomorrow.
I can already do changes.
Why would you say
I
such
can
things
already
to
do
me?
changes on.
It's not very nice.
Let me make sure.
Right now.
Okay, your name is on here. I will fix that.
I'm not so sure of that. Yes, you did. Sharon would have been.
Yeah, I had no idea.
Let me check. So you needed that added to. I will add.
But I did it quick. I didn't know.
Because there's a natural curve built into all tests. The curve is basically, it's however many marks it is, and then I cut a certain amount of marks off that are like the hardest marks. So like this is 33, 5 marks are considered hard, and the 100 is at 28. So anything that's 28 or above is 100%, not even without steering or anything. So does that make sense? So you get a raw score, and then you get a curve score.
I got 28.
It's different than the mock exam. You take the mock exam, then you get level A. And then you'll see, oh, okay, I'm averaging an A level, C level.
Come on, man.
Hold on. I'm looking for my writing
I
project.
think someone was not.
Yes.
Good afternoon, Golden Lions. This is 7th grade and your afternoon announcement. Students, please remember to check your Cambridge email daily and report to school with proper CIE uniform. Make sure your outerwear is solid white, black, or red. Also, please wear your student ID badge on your neck. Attention to the issue. Do not ignore
This is for you.
policy. Tonight is CIE's open house. It will start at 6:30. We look forward to seeing all of our Golden Lion families.
They figure out what I do.
Square planner.
Date of purchase on OSB is September 7th.
It's the one I got. Square planner. Yes. That's it.
I feel bad, but I also think
Nominations will be on it. Nominee reviews t-shirt, certificate, or sticker, or please remember to wear your ID every day. To receive a replacement ID, you must pay for it on OSB. Students who have unpaid balances will not be allowed to participate in field trips. Attention all students, all students must have the Hero app downloaded on their phone. Yeah, you know,
Yeah. No, this is on the paper. Listen.
this concludes our afternoon.
One last announcement, attention 9th grade class. I have the results to the freshman student council. For the 23-24 school year, your class representative is Liam Diaz. Your treasurer is Erica Patterson. Secretary is Rhea Fernandez. Your vice president is Maria Flores. And for the first time ever in CIE history, we had an exact tie for freshman class president between Christopher Candilla and Jenny Zuniga. So freshmen, check your emails today. We will have a runoff between those two candidates, and I will announce those results on Friday. Have a great day and good luck.
How are you doing? being brand new.
This time it wasn't me. I know. Oh, Lena, imagine knowing someone that's hardworking. Me personally, I would never.
I don't like taking a safe picture.
That's silicone. You get it? That's silicone. You get it?
Alright, have a nice day, everyone. See you all Wednesday, unless you're heading back to take an exam right now.
Be careful on the bus.
Good luck to those of you taking an exam right now. Just wait outside for a minute so I can go use the bathroom.
You're gonna be in your house, right?
Yes.
Generator.
I will be here for a little now. That's today. Your family's coming?
Yes.
Are you gonna have lots of questions?
I think so.
Are they worried?
No, they're not that worried. Because I showed them my grade in this class, so they're not that worried.
No, I'm really
I think you'll be alright. You just have to study. So far, so good, right?
Yep.
Just gotta keep up with it.
Yeah.
Remember, you don't get a estimated level like you don't get estimated level until you take the first quarter.
Okay.
But you're doing okay so far.
Yeah.
Bye, Miss Lee.
Hi.
What?
That's diamonds.
Oh yeah, that is. Never mind. I'm just.
Which diamond do you want me to talk about?
There's
I've got several diamonds here. I've got the molecular structure of diamond, and I've got real diamonds. Like which one? Like diamond on my hand,
Oh.
and I've got diamond here.
Confused.
Like-
there's multiple different.
Yes, there's multiple diamonds. No. This is diamonds.
Oh,
This is the molecular structure of diamond. That's what I meant.
I was about to be. No way. There's different molecular.
No.
structures of
There's
diamonds.
not. I'm just saying that. Aha. Which
Oh.
diamond do you want to see? The real diamond, or like the plastic molecular structure version?
Molecular structure. Have a nice day.
We go over diamond later this unit actually, because we have to talk about how things are structured. So we do get to go over diamonds. Diamonds and graphite. All right. For those who need to take a test, yes.
I have a question.
Yes, you may ask.
Who is one of the best kids that is still in the school? We have this competition coming and
Has to be biology though.
Arts.
I would. Oh, 'cause, you know, it's funny because everybody I've ever talked to. It's a great question, but everybody I've ever talked to who's actually ever taken it says it's pretty much all biology. So, Mohammed is really good.
I know that's. Oh, we're actually gonna leave now.
He's okay at the name of the
So
chemistry.
then I can have to stop playing Pac-Man.
Still here.
Yeah.
Don't use my Pac-Man.
I would say go for it.
I'm still good at Pac-Man.
Sure.
He's another number. He might
I
be
actually go professional, honestly.
aligned at a couple. In first period, talk to me in first period. That's actually the class you want to pull out because that's A level. So like those are third year students. All right, if you're here to take the test, please hold on. Let me go to the bathroom real quick. You can ask real quick. I just.
just trying to give her like a boatload while she passed.
Gene or
I don't know if she died in pain.
like, where are you getting to?
My surface level research has told me that nitrogen is cheaper than morphine. I was thinking for like people in hospice or in the hospital dying from like that there's no way that they're gonna survive and that they're just gonna like die for sure and they're gonna be just do it early on their terms.
Can you imagine having that as a global, global perspective? I would run that by Goodman too. She would be able to like, that's a lot of the ethical. I mean, there is ethical.
I feel like
You're talking pro euthanasia.
yeah.
That's literally what.
I mean, they do it to dogs, so I mean, personally, okay, no, because like
Humane euthanasia.
when you put down
That is quite controversial.
when you put down a dog, it's not because you want to get rid of it. It's because it's a thing. There's no way to save the dog.
I mean, so you could discuss the science, but
So like I'm saying.
you can't discuss the politics. You can talk about what is possible, but not what is like. You're not supposed to like manipulate what is the right thing to do.
Personally,
Because there's like arguments there,
yeah.
which is where I said in global, you may be able to debate a topic like that.
For hours.
Project.
Come on. It's a good topic. Think about it. Think about how many lives.
It's a controversial topic. We'll talk about that.
Peacefully. Would you rather die in pain or die peacefully? Just getting a little bit, just a little bit of.
You gotta take a test.
I would rather, if I know I'm gonna die for sure, I would rather.
And you're not alone. You're not alone in this. But I'm just saying that that's a tough topic.
Personally, I would do that.
Yeah, it's an ethical thing. It's the value of your life. Idea? Oh. That's Sophia. Isn't that the Sophia project?
Yeah.
We'll talk to about. We'll talk next week. Next week at the Ninja. This week, no meeting this week. We have one brunch this week. Sign up for those who sign up, and then next week we have a meeting for the Ninja. Okay. You're welcome, and good luck sorting through all of that. Go ahead, Ash.
If somebody missed, how much money is
Woo! Depends on if it's AS or A. It's in the hundreds of dollars. Both? Yeah. I think it's like a 190 or something like that. It's high. It's almost $200. AS is like 110 now. Yeah. That's approximate. For who? Oh, for the parents. Okay. You know, maybe Miss Huffman can use that. Yeah. What are the current prices? Let me see. Money. You feeling better? You ready to knock this out? You feel pressure? No pressure. Do your best. And it's not like I'm going to go back and say anything if anybody doesn't. Everybody just knows the class did amazing. Don't stress yourself, okay, Sophia? I believe in you. Believe in yourself. That's the important part. You got to believe in yourself. Oh, George was supposed to come by.